I forgot to press start stream, go figure. Uh, Today we are going to continue talking about acids and bases. We're going to do some fun calculations with some of these, using some of these acid-base concepts, which are pretty much the same as the equilibrium concepts, but in a new context, I guess. Yeah, we're going to be continuing on with this. So, hi, little dude. You want to come up here? Okay. Oof. Okay. So, as I mentioned, I finished grading the exams yesterday. And so, for the non-honors people, I adjusted your scores by making the maximum points fewer, but keeping your raw score the same, so your percentage would go up. And then the honors people was not. It was, you guys were fine, so no need to fix anything there. So, other than that, I did put comments in all of your things on Canvas. I don't get a notification if you respond to those, so if you have something to ask or want clarification on, shoot me a message in Discord or message me through Canvas, since it won't tell me if you actually comment on those things for whatever reason. So, just so you know, I'm not going to be able to see that unless you tell me that it's there. So, cool. Cool. Any questions on that or our acid-based stuff from last week? Anything we need to go over there? Alrighty. Then let's just start off with a problem. All right, so let's say we have a solution of, let's say 0.25 molar hydrofluoric acid. And I wanted to find the pH of this. So hydrofluoric acid is a weak acid, meaning its Ka is not going to be way greater than 1. Let's go ahead and did I put that in Discord? I didn't put our table of acids. Okay, let me. Well, I'll do that later. Let me just look up this one. HF hydrofluoric acid. Okay, its Ka is, or you know what? I have on Wikipedia. It's pKa, so we're gonna calculate its Ka. So its pKa is 3.17. So, it's good practice. We'll do both. If we have its pKa, we can find out the Ka, right? To go from Ka to pKa, we took the negative log of the Ka. So to go backwards, we would do the anti-log, or 10 to the negative pKa. So the Ka would be equal to 10 to the negative 3.17, which is equal to 10 to the 3.17, negative 3.17 rather, is going to be 6.76 times 10 to the, what is that, negative fourth power. And with this number, we only have 2 sig figs anyways. Alrighty. Hopefully that's okay. So that's how we can calculate Ka if we're given pKa. Just like before, we're essentially asking, this question essentially is asking, what is the H plus concentration in the at equilibrium? So this means that we need to do an ice table. So for a Ka, acid dissociation constant, that tells us that we're going to be looking at the equilibrium from our acid as the reactant, dissociating into those ions. So Ka always follows this form. You don't see it in reverse. So Ka always has your acid as your reactant, the H plus as your product, along with the conjugate base. So Ka is going to equal H plus times F minus. Actually, I should. Well, I'll write the expression down, but I'm gonna get rid of it because I realized we have to do our ice table. So let's go ahead and just get rid of our expression for right now. We'll use that in a little bit. All right. So if we're gonna do an ice table, we want to put in as much information as we have. The only thing that we have is that we're given 0.25 molar HF. So we're going to assume at the beginning we don't have anything else. Technically, we have a hydrogen ion concentration of 1 times 10 to the negative 7, but we're going to see that that's not going to really be relevant here. We don't have to worry about that because that's going to be so small compared to the H plus coming off our acid. Water is a super weak acid, so. All right. We're always going to see that because we only have HF, obviously we're going to be producing our products. And so our equilibrium concentrations would be these. And now we have our Ka expression here, which tells us we're going to have x squared over 0.25 minus x is equal to, what was it, 6.76 times 10 to the minus 4. And so we would then go ahead and solve for this. I'm going to tell you a little shortcut, though. Very often, the concentration of your acid is very, very close to your initial concentration that you started with. That means that we can kind of just ignore this guy. We're going to see often with sig figs this assumption will be valid. And so just the caveat here, we can assume this if x is less than 5% of your original concentration of your acid. And by and large, most things are going to be there. So Kevin has already calculated this for us. You've calculated x? Okay. So in this case, x is going to be equal to 0.013, which is definitely going to be, well, let's see. Is that going to be, let's see what that'll be in terms of percentage. 0.013 divided by 0.25. That is going to be higher than 5%. So in this case, we can't ignore x because this assumption was invalid. So Kevin, was that done using a quadratic equation, or was that done by assuming that x is less than 5%? My guess is quadratics because you had already done it by the time I did it. It is assumption. Okay. So if we assume that the 5% that we can get rid of this minus x, we see that we get x is 0.013. If we do that, or if we just divide that by our initial concentration, we're going to see that we get 0.052, which means we cannot ignore it this time. All right, so you always have to check your assumption if you were to just solve x easily. Because if you do solve x easily, just x squared over 0.25, very easy to solve for x. You would just take the square root, move the 0.25 to the other side and take the square root, easy. But in this case, we can't make that assumption, so we're going to have to do it the long way. So let's go ahead and plug this in to our Wolfram alpha. Or you can do your quadratic equation. Though I did notice that a lot of you did have mistakes using the quadratic equation on your exams. So I'm going to just show you. You don't even have to simplify the equation if you want to use the Wolfram alpha. You can just plug it in directly. So you can say we have x squared over 0.25 minus x equals 6.76 times 10 to the negative 4. You can just plug it in directly like this. You don't have to simplify anything or anything like that. You hit solve. It's going to give you your crazy fractions, so you click simplify forms, and we're going to get our real answer, which is going to be 0.012 instead. So go figure. Since our assumption mode was very close to 5%, we're going to see that x is just going to be a little bit less than that. Oops. And even with sig figs, it's going to be 0.13 anyway, so it doesn't really have a huge impact here. But let's go ahead and solve for that. So if that's going to be our x, that's going to be our H plus concentration. And so if we want to find the pH of the solution, that's the negative log of H plus. It's the negative log of all this business, which is going to equal to negative log 0.012666. And so we get 1.897. If we only want 2 sig figs, that'll be 1.90 with 2 sig figs. And so that would be the pH of our solution there. All right, so we'll see that's going to be the case for this. All right, so that's why we can also kind of ignore that amount that water would give. So if this is the H plus concentration from our acid, from water, 5, 6, 7, we can see that the amount that the water would give is negligible. It doesn't even come close to putting in where our sig figs would be. So we're just going to completely ignore any H plus that comes from water itself because it's just going to be completely negligible. Oops. And so that's just going to make things easy for us. So if you're working with like super dilute acids or super weak acids, yeah, sometimes the H plus on the water might become important, but for this class, we're just going to ignore it. So lucky us, we don't have to think about that. So we're going to assume that all of the H plus in our solution will come from our acid. And so we'll go through it that way. Alrighty, cool. Any questions on that one? So just to kind of summarize, we were given the concentration of our solution as well as its pKa, which we were able to calculate the Ka from. This question was essentially asking what the hydrogen concentration was at equilibrium. And so we solved for that using an ice table. In this case, we were not able to just get rid of that minus x portion because it turned out to be more than 5% of our initial value. So we had to use our quadratic equation there to get our real x value. And then we saw that we could take the negative log of that to get our pH. All right, and just thinking about it, does this kind of make sense? Yeah, right? This is a fairly concentrated solution of a weak acid, so we're seeing a pretty low pH, which means it's pretty acidic, so that makes sense, right? If we're getting some super high pH, that's probably letting us know that we did something wrong somewhere in there. So, always keep these things in mind of what a reasonable answer is. Cool. Alrighty. We can also find something called the percent ionization of an acid. And that would just be the hydrogen ion concentration at equilibrium compared to your initial acid concentration. And since it's a percent, of course, we'll throw our 100% at the end there. And so if we wanted to do this for this particular one, we saw that that would be 0.012 over 0.25 times 100%, 0.012. In this case, we get 5.1% ionized. So at a given time, 5% of the acid molecules exist as separate ions, and the other 95% of this acid remains as molecules. So we're going to see that only 5% of this acid will dissociate at a given time. All right. Of course, we can see here that actually we'll be okay. That's it. We don't need to look at this further. All right. Any questions on that or on the previous part that we did? I guess I should say acetic acid. pKa of 4.78 at a given temperature. Vinegar claims to be 5% acidic, and it has a concentration of 0.833 molar. Is this claim true? Is our vinegar indeed 5% acidic? Let's find out. So much like before, if you actually go to look at a bottle of vinegar, it'll say what percent acidity it is, and then you can calculate its concentration, which is pretty cool. And so we're going to kind of evaluate this. So let's say that I figured out that the concentration of acetic acid in my vinegar sample is 0.833, and the bottle says it's 5% acidic. So let's go ahead and see if that's true or not for this particular one. So again, I've given you the pKa here, so we should probably go ahead and convert that to Ka. So we'll get 10 to the negative 4.78. It's going to be 1.660 times 10 to the negative 5. And it looks like we have 2 sig figs there. Hopefully that part's okay at least. So we have our Ka. We're using acetic acid this time. And so our equilibrium equation would be acetic acid breaking into hydrogen and acetate. And so now we can go ahead and throw in our ice table. So this is going to be much the same as what we did before. So this time we're starting with 0.833 molar and nothing of the others. Just like before, it's obvious Q is definitely going to be 0, right? 0 over 0.833, so we don't have to worry about it. We know that it's going to be way too small, so we're going to be shifting towards the products. And so we would complete our ice table as follows. We'll go ahead and say Ka is going to be x squared over 0.833 minus x. Let's go ahead and try our cheating method here. Let's say we're going to assume that this is just x squared over 0.833. And that's going to be 1.6 times 10 to the negative 5. If we do this, let's go ahead and do that. 0.833 times 1.66 times 10 to the negative 5. And then square root that. So x would be 0.0037192 sig figs. Let's just double check our assumption here. Is 0.0037 over 0.833. That seems to definitely be okay, but let's double check. Yeah, that is 0.4%. So we are okay. We can use this assumption. So we don't have to actually calculate the hydrogen ion concentration normally. So that would be our hydrogen concentration. And so Kevin's already done it, but let's say the percent ionization will be the H plus at equilibrium over the initial acid concentration. And in fact, our assumption here has already kind of, we did this exact calculation. So if it's less than 5% ionized, we're allowed to use this assumption. And so by doing this, we do indeed see that it will be 4.5% with appropriate sig figs. And so if we just had to round this to 1 sig fig, though, it would just be 4%, right? Because we would get, technically 4.46. And so these people are liars. You can definitely do it the regular way. You're going to get a more accurate answer. I would applaud you for doing so. But if you are lazy like me, you can use the assumption. So you can use the assumption, you do not have to. So, but if you do use it, you have to check. So that's the take back there. All right. Cool. So the people are liars. With sig figs, their vinegar is actually only 4% acidic if they want 1 sig fig. So we're going to sue them for false advertising. And we're going to make a lot of money. Okay? Hooray. All right, let's do stuff the opposite way. Let's say a sample is, an acid sample is 7.26% ionized. If the Ka is equal to 4.82 times 10 to the negative 4 molar, what is the original acid concentration? And by that I mean HA, whatever acid this happens to be. Mystery acid with this particular Ka. So, we can figure this out. As always, using our skills of logic and deduction here. So, we know that we ended up with if we ended, oh gosh, let me put this in percent form. We know that our H plus concentration over our HA concentration was equal to 0.0726. Right? We also know that H plus times A minus over HA equals 4.82 times 10 to the negative 4. And further, we know that every time we dissociate this acid, we get one H plus and we get one A minus. So those two would be the same, right? So that would just be H plus squared over HA. And so we have a system of equations here. We can solve for this rather. We can say, okay, H plus is 0.0726 times HA. And therefore, 0.0726 times HA squared over HA equals our equilibrium constant. Just substituting in what H plus was into that. I took this H plus and plugged it into that equation there. We see that we have 0.0726 times HA equals 4.87 times 10 to the negative 4. And solving for HA, we get, let's see, 4.87 times 10 to the negative 4 divided by 0.0726. We get 0.006708, we'll say. But just note, this is technically the equilibrium concentration. And this one is earlier, this is technically the initial one. So I probably shouldn't have been able to cancel those out. But let's make the assumption that we can make them relatively equal to each other. Let's see what our HA would be. So technically, right, this would be HA minus X if we're looking at the initial one to get the equilibrium one. So we're kind of making that assumption that we're, well, I guess we can't because we have 7%. Fine, forget it. We have to do hard math then. My apologies, because we can't cheat on this one. All right, sorry. Let's backtrack here. Sorry, guys. I wanted to lie to you and cheat, but not going to be allowable this time. Okay, so that's HA minus H plus, which will then be 726 HA. Okay, there. Now we can do this thing. So now we can solve this just like before. We'll have 0.0. Oh goodness. Let's solve this nonsense. Can I just place these with X's? Would that be okay with everybody? If I do that. 0.00527x squared over 0.9274x equals 4.87 times 10 to the negative 4. All right, cool. Good. All right, solve for x. Quadratic or cheat using Wolfram alpha, which is definitely what we're going to do because I don't want to calculate any of this stuff. Okay, let's see. So our equation 0.00527x squared divided by 927.4x equals 4.87 times 10 to the negative 4. Okay, what do we get? What do we get? Let's hope making up this problem. Variable x is not present in this. Oh, I see. Okay, I didn't put a parentheses where I should have. Or actually, I have caps lock on. It's thinking these x's are something else. Okay. Sorry, I typed that in wrong. Okay, here we go. Approximate this to, we get 0.085701. So now we can finally do this business. So we know that at equilibrium, the HA was equal to, where's our equilibrium one? Our equilibrium one is going to be the HA minus X, right? Is going to be your HA initial minus X. So now that we know what HA at equilibrium was, now that we know what X is, we can solve for our concentration after the fact. So let's go ahead and do it. Let's go ahead and plug in. Wait a second. X was HA. I'm so sorry, guys. X is HA. I really should have written equilibrium on these. That is HA at initial. So actually the X value we've calculated is our initial one already. So thank goodness we don't have to worry about calculating anything from this. We can calculate its equilibrium concentration if we want, but this is important that you always label things unlike I just did. That's why we stumbled a bit here, but that would be your HA initial. So if we're going to take a look at our concentration with sig figs, how many sig figs do we have for this problem? Looks like 3. So let's go ahead and say that HA was equal to 0.0857 molar. That's what we started with. So that is our initial equilibrium there. All right, so what have we learned? Always label your bits here because otherwise you're going to get confused. So we win. All right, any questions on that one? All right. Let's see, what else can we do with this fun stuff? Actually, I think that's probably good for practice on those. Let's move on to our next little bit here, where we talk about polyprotic acids. So these will have multiple Ka values. So if we take a look at, for example, carbonic acid, that would dissociate into a hydrogen ion and the bicarbonate ion. And if we take that bicarbonate ion, we can break it further by removing a second proton. For this one, we would have 2 different Kas. That would, of course, be experimentally determined, looking at the concentrations of these. Whenever we have polyprotic acids, we're going to see that your first one will always be bigger than your second one. And if you have a third one, of course, or however many protons you have, your first one is always going to be the most acidic. So removing that first proton will always be more favorable than removing the second one. You don't lose 2 at once. So you're going to see that we can work with this. So just as a generic rule of thumb, if if you were to see that this is going to be greater than 10 to the third power, then we can kind of just ignore Ka2. And any subsequent ones. We're going to see that that'll be the case. We'll look at an example of it. We'll look at this carbonate and bicarbonate example. And we'll be able to see if this assumption is going to be valid or not. Otherwise, if we can't ignore it, we get to do 2 ice tables. How exciting! We would have to do an ice table for each one. So, if we look at our first ice table, that will be the first decision. Let me find the I've got the PK or the KAs here. Let's see. Okay, blah blah blah. Where did the Ka go? Okay, Ka1 is 4.3 times 10 to the negative 7. And Ka2, where did that one go? Ka2 is 5.6. Let me just write this one down somewhere here. Okay, here we go. 5.6 times 10 to the minus 11. Alrighty. So we'll just keep that there for later. We'll have it later. So let's say we have the maximum you can dissolve for carbon dioxide and water would give you carbonic acid concentration of 0.0037. So, all right, Oz, I'm going to put you on the couch, little dude. Okay, there you go. All right, so let's go ahead and take a look at what this is going to look like. So we're going to start with 0 of both of these guys. And we'll say we have this amount of carbonic acid. As always, for our ice table, we'll be subtracting x from our reactant. We'll have x on the product side. We'll have our x squared over the second part equals 4.3 times 10 to the minus 7. Let's make our assumption, see if it works. Let's see if we can do this. So x squared over 0.0037. Let's see what x is going to be here. Alrighty, let's see. 0.0037 times 4.3 times 10 to the negative 7 will be 1.59 times 10 to the negative 9. Really, really small. We can see right away that this number is going to be much, much smaller than 0.0037. But we should do it anyway. Let's try it out. Over 0.0037. Let's just double check. We're going to see that the ionization here is super small. So 4.3 times 10 to the negative 5%. Definitely less than 5%. So we can make this assumption. Cool. So we can say, although in this case we probably should not ignore the hydrogen that's coming from water because obviously this is super tiny. But let's just go ahead and see what's going to happen here if we take a look further along with this. All right, so actually, did I write the right Ka here? Ka is indeed 4.3 times. Yeah, okay, cool. So if we now take our second ice table and break down our bicarbonate further, notice this time we're going to be starting with some bicarbonate in there, as well as some hydrogen ions. We have that from our first dissociation, right? So if we're going to do a second ice table, we're going to do the same thing. Oops, plus X here. Obviously, again, our reaction quotient would be 0, so we know we're going to be moving in this direction. Plus X, sorry. And then that'll be just X. So technically, we will end up with the following expression. What was our Ka2? It was 5.6 times 10 to the negative 11. All right. If we make our assumption here, if we make the assumption that 1.59 minus x is the same thing as 1.59 times 10 to the 9th, we'll see that if we assume, if we make the assumption, we'll get x equals 5.6 times 10 to the negative 11, right? That crazy exponent thing will cancel out in the numerator and denominator, because subtracting x and adding x, we're assuming it's not going to change the number. And let's go ahead and see what that would be. Let's see if 5.6 times 10 to the negative 11 is a valid assumption here. 5.6 times 10 to the negative 11 times 1.59 times 10 to the negative 9th. Aha, that is 3.5%. We are allowed to make it. Assumption is valid. So we're going to see that we're going to end up with a hydrogen ion concentration at the end of the day that is going to be much, much smaller from the second dissociation than it was from the first dissociation, right? It's less than 5% more. And so as a result, we are allowed to just say, forget it, we're not even going to consider this second Ka. Because this is so much smaller. So let's just look at this again. From the first time we did it, we got H plus equals 1.59 times 10 to the negative 9th. From doing it the second time, it's second dissociation. Plus 5.6 times 10 to the negative 11. If we're gonna, let's make this kind of the same value here. That'll be 0.056 times 10 to the negative 9. And we're gonna see this is really not gonna change our number too much. So technically we'll get 1.65 times 10 to the negative 9 instead. And so it'll be very, very slightly bigger than our original value. For us, we don't really care if it's just that slight difference. As you can see here, the difference is a difference of 0.000000000. How many is that? It's 8, 9, 10, 11. That's the difference there. So does that difference really matter? Maybe. For us, no. We're going to assume that because, again, it's less than 5%, we don't have to worry about it. And because if we just look at the Kas, we're going to see if we look at the Kas themselves, 4.3 times 10 to the negative 7, 5.6 times 10 to the negative 11. If we do this math, of course, we're going to see that we're going to get greater than 1,000. I assume, I guess I should actually do this first. Divided by 5.6 times 10 to the negative 11. We do indeed get 7 point whatever 8 times 10 to the third. It's bigger than 10 to the third, so we can just assume that we don't have to worry about doing a second ice table here. Okay? The H plus from Ka1 is sufficient. All right, so we do not have to worry about doing the second ice table for this. All right, there was one thing I wanted to talk about with this. Oh, also, notice that this X here, that X is also the concentration of carbonate there. So if we were to look at kind of what's happening overall, if we were to look at this, we'd see that we had some amount of carbonic acid. We had the bicarbonate. And then we had the carbonate, right? Those are kind of the three species that we have here. We saw that this one didn't really change. We saw that this one didn't really change. But we do know that this one, what was it? 5.6. Oops. No, go away. We're going to see we have even less of that second one. But notice also that because Ka2 was so small relative to Ka1, that the concentration of A2 minus was just equal to our Ka. So that's a shortcut you can use. So if you are dealing with a diprotic acid, and so because it's so small, we're going to assume that the concentrations of the, I guess now monoprotic form, along with the H plus, are just going to be big comparatively. So we can make this assumption as well. So there's a lot of assumptions we make with this acid-base stuff, but there's shortcuts that make things happen faster that we don't have to worry about too much. While in this case, it does look like the H or the hydrogen ion concentration from water would completely overwhelm this stuff anyway. You know, this would be kind of a futile exercise. That particular concentration of carbonic acid is so small that it's just not going to be really important for us. So if you were to just take some water, pure water, and leave it out, have some carbon dioxide dissolve in it to form H2CO3, you're not going to really notice any acidity happening there. If you wanted to make your carbonic acid actually be acidic, you're going to need to throw in a lot more than would normally dissolve. You'd have to pressurize it like a soda can would be acidic because you're throwing in a lot more than CO2 than can normally dissolve in your water. Okay? How exciting. All that work for nothing. Alrighty. And so this assumption can also hold, by the way, for Ka3. If Ka1 and Ka2 are less than 10 to the third, but Ka2 over Ka3 is greater than 10 to the third, we can ignore Ka3. All right, so if that were the case. There are not too many triprotic acids, but if you were to encounter something like this, the same assumption would hold when you're comparing them. And so only 2 ice tables would be necessary here. All right, so you would have to do an ice table for Ka1 and Ka2, but you would not have to worry about it for Ka3. All right. A lot of information here. Just kind of knowing when you can use these assumptions. Again, they're just there to kind of save you some time. So, that's pretty much all I wanted to cover today. We'll finish it off tomorrow, and then we'll start our kind of next section. Any questions on any of this acid-based stuff? I'll put up your homework later today so you can get started on it. Actually, is there even much left in this chapter? Probably not. There's probably not too much left because maybe titration curves is kind of the last little bit that we'll talk about with this before we move on to the next chapter. So, cool. Yeah, I'll go ahead and throw up your homework. If you have questions, you can put them in Discord. But yeah, awesome. I will, I guess, see you guys tomorrow. Enjoy your Monday.